All right, recorder is recording. And we'll start with answering any questions that might relate to exam one on Wednesday. Yes.
I did the practice, or I did an exam that was just one semester before, and I noticed there was one question about it had to do with like.
Doubles?
Yeah, well, I was assuming those aren't on the.
They're not.
Okay. But
Right.
Then, there was another question that had to do with. Actually, I have it here.
Okay.
It had to do with computing K20.
K20, yes.
Yeah, and it was like assuming. Let me see here.
Okay, so let me get to the test first. So it's the semester before?
Yes, the
Okay.
semester before the one you did in class.
Okay. All right, so let's go there. Go to the shared folder. Old exam one. There we go. So it's the 1189.
I believe so. Yeah.
Okay, we'll take a quick look at it.
And then it was question 4 of 7.
Okay.
I was just confused on how you would even reason this out. Like, I was trying to compare it to what we did in the lab,
Okay.
and I'm like, man, maybe I made my K circuits wrong, because all of the K for the last OR gate, my OR gates just took in 2 inputs. And it was consistent throughout every K1, K2, K3.
No, because your K3 actually has 4 inputs. Okay, so let's go ahead and take a look at the notes, okay? Because what we need to do is to find out which part of the notes is relevant. And I think all right. So we go back to the notes, and it is the big OR and the little OR after that that is important. So we need to go to binary addition, okay? And go all the way to section 6 and go all the way to the generalized equation here. Okay. Okay. So in this particular case, we if you're looking at K20, so that means n is what? N is 19. Okay. So when n is 19, we have a big OR loop here where I goes from 0 to 19. So how many iterations do we go through here? We have exactly 20 iterations. So for each iteration, there's a term to be ORed with the rest of the other terms. So there are 20 terms right here, and then plus one last term that is not a part of this big OR. So we have altogether 21 terms when n equals to 19. Is that making any sense?
It makes sense here. It's just that I'm thinking about it in the terms of what we did in Logicem.
Okay.
And I'm just looking, like, I could show you my K3. I have it printed out for my notes.
Okay.
It just doesn't resemble anything like that. Like maybe
So let me take
maybe it's something I need to ask you at office hours. Like,
well, let's see.
K3 is
So your K3 is making use of K1 and K2, and that's why there's a problem. Because if you make use of K1 and K2 in your K3 circuit, then you're defeating the whole purpose of using carry look ahead. Your K3 circuit is supposed to be not, okay, this is what your K3 circuit should look like. Not this. Is that?
So I just completely did this wrong.
Well, you kind of missed the point of using the carry look ahead mechanism, because the whole idea of carry look ahead is to reduce or get rid of the dependency of Ki depending on Ki minus 1.
Right. But maybe I have this wrong. But I'm not feeding K1 into K3. I'm using a splitter to get. Do you see what's happening here? Like, I'm using a splitter, and then I'm running it through the same logic that it would be.
But you still can see that you have the levels of logic. It's still going to see how this fits into here, and that fits into here, and that fits into here. So you're still cascading. You still have a ripple effect. It is just that you're not you're not using the ripple as a normal carry ripple adder, but as the number of as I increases, okay, as this index increases, you're still making that chain longer and longer,
Okay.
which is exactly what we're trying to avoid by expanding K2 into this big long term and then use distribution so that we end up with only one level of AND gate and one level of OR gate when we already have PG and K0.
So the way to fix this in Logicent would be to have these two gates take more inputs, and that's what you're.
Correct.
Okay.
Yep. So what I can do is, I cannot do it in class because I got other things scheduled for this class. But what I can do is, when I get back to my office or during the lab time, I can kind of record the solution to the binary, the 3x3 carry look ahead. And I'll even throw in the subtractor stuff and also the flags. Yeah. So are there any other questions related to the exam on Wednesday? Yep.
So I actually have a couple questions for another student, but we were working together.
Yes.
Okay. So
But as long as it's related to the
yeah. So one of the questions is in module 0295.
Mm-hmm.
How does the proof involving the I and the P in the unsigned comparison section work?
Okay, so let me get to the section first. Which module?
0295.
0295, binary number comparison. Okay, so I don't think it mentions P and G in here.
Or P and I. It's
Oh,
like,
P and
as
I.
a sub index in the unsigned comparison section.
Unsigned comparison, you mean here? Okay.
Yeah, here.
Okay. So, so this proof is informal. Okay, so what it says is, the question is, what can we use? What can we use to indicate whether x is less than y, unsigned? Okay, so that's the question. So what we'll do is this is basically a very informal proof to basically say that, if I is greater than some p, we assume that xi and yi are the same. So let's say you have a 32-bit integer, okay? So, and p in this case would be 31 to start with, because you only have 32 explicit bits from bit 0 to bit 31. Well, you actually have an infinite number of bits from 32 and up, except those are all zeros, okay? So we can make this assumption of, when we have a 32-bit number, p can start with 31. Does that make sense? Okay. So now we look at just bit 31, which is what p is. Okay, so assume p is 31 in this case to compare two 32-bit numbers. So what we do is we focus on that one single bit, which is x subscript 31 versus y subscript 31. Is that okay? And that is the most significant bit that can differ between the two numbers. So in that case, if xp is 0 and yp is 1, then we can make a conclusion and go like, yep, we know which one is bigger because y has to be bigger, right? On the other hand, if xp is 1 and yp is 0, then we know that xp is larger, or the number x is actually larger. But either way, we have a conclusion, and we can just exit the loop because now we know the ordering between x and y. Okay. But what about the case when xp and yp are exactly the same? Well, in that case, we first check, are we already looking at bit 0? If we're not looking at bit 0, then we decrease p by 1 and then go back to the beginning and then we work again. In other words, we start looking at the most significant bit, which is on your left-hand side. We move to the right-hand side one bit at a time until we find a bit that is different. Does that make sense? Or until we get to p equal to 0, and yet we see no differences between the two numbers, then we conclude that the two numbers are the same. And we still have a conclusion that x is not less than y. So this is just based on how we interpret numbers in terms of okay, we start looking at the more significant bits and then work our way to the less significant bits if the more significant bits are the same. Is that part okay here? So that's basically what P is an index of which bit are we looking at.
Yeah, we were just wondering like why you used it instead of using just I.
Okay, so the I is here to qualify, all the bits to the left of bit P are assumed to be the same. Yep. So that's what I as an index is for.
Right, and then P is like when you have like some like P number of bits.
So P starts with the most significant bit position given whatever width that you're given with. So let's say let's say we're dealing with 4-bit numbers. Then P would start with 3 because we count from 0. So bit 3 of a 4-bit number is the most significant bit. Is that okay? All right.
And then
Yep.
in sign value subtraction, what bit in the answer is the sign bit? Is it in the same position as the sign bits in minuend and subtrahend?
Yes. So the bit always refers to the most significant bit of the pattern.
And that was it.
Okay, great. Any other questions? Yep.
I have one. It's kind of a little bit of an overflow. So
Uh-huh.
when you compare, and there is an overflow, do you change the sign bit or no?
We make use of the sign bits, but we do not change the sign bits.
So the overflow is just to show you if you can trust the comparison or not.
Whether you can trust the sign bit.
Yeah.
If there's an overflow, the sign bit would indicate the actual opposite of what it should be indicating.
Okay, so it is the opposite then, if there is an overflow.
If there's an overflow, then the sign bit is opposite to what it should be.
Okay, thank you. That's what I was asking.
Okay, great. Any other questions? Okay, no other questions? All right. So if you don't see a video later today, like I will give myself until maybe 8 p.m. or so, send me a note, kind of nudge me and go like, okay, you said in class that you would actually finish the 3x3 adder, okay, with the modification to turn it into both an adder and a subtractor, and also throw in all the flags. So there will be some output pins, one for B, one for O, one for L, one for, and so on and so forth. Okay, so I'll do that, but not during class time. Okay, any other questions related to exam 1, which is on Wednesday? Okay, we are good so far. If you do have any questions, don't hesitate to ask. But for the time being, I'm going to switch back to, okay, let me just get rid of some of these unused folders. And we'll switch back to doubles. Okay, so starting today, we'll be focusing on a new topic, more or less, that talks about the double representation. The double representation, is in here. It's floating point number representation. I hope some of you have time to read a little bit ahead of me because that would totally help speed up the process of you understanding the material. So we'll start with let's not start with this, okay? Because this stuff looks, there's a lot of notation here and it can look confusing. So let's start with the rationale of a floating point number representation. Okay. And let me ask you, what is the speed of light? Okay, we'll look it up. Okay, so and I'll relate it back to the current topic. So we'll look up speed of light. Okay, and you will see the speed of light is 299,792,458 meters per second. Okay. So let's say you're in a science class, okay, and you're required, to use the speed of light to do some computation. In most classes, okay, I would say, just to get a order of magnitude, it is probably good enough to say this is 2.998 and then some units, of speed. Is that okay? All right. So let's say your science teacher says, I only need you to have four significant digits, okay, in your calculations. Is that okay? Are you going to enter the entire number every single time when you need the speed of light? Let's also make sure that we assume that your calculator is not one of those fancy ones that already has the speed of light as a constant that you can just punch in. It's a one key thing, right? Nope, your calculator doesn't have that. Your calculator doesn't have any memory feature either, so you cannot just recall, okay? So what are you going to do? How are you going to enter the speed of light in a physics class so that you can calculate, what is the energy of a particular mass, like E equals mc squared, right? So how do you enter the speed of light? Using an approximation. So let's just say that, I can even let you use just approximate it to 2 digits of significance, okay? Like 3.0 in this case. But it's 3.0 times what? Time 10 to the, exactly, times 10 to the 8th. So how do I know that? Well, because there is an implicit point here, right? It's just that, we usually do not need to know the fractions of a meter per second when we're calculating, the speed of light. Are we okay so far? So there's an implicit point here, and as I move that point to the left-hand side, what do I need to do in order to maintain the value that I'm representing? If I move the decimal point once to the left, what do I need to multiply in order to maintain the value? I have to multiply by 10, right? 100, 1,000, 10,000, 100,000, 1 million, 10 million, 100 million. Is that okay? So this value can be known as 3 times 100 million. Is that okay? Okay, so on your calculator, okay, if you have to enter 3 times 100,000, that doesn't really save you a lot of keystrokes, does it? So what can save you a lot of keystrokes on a calculator? Exponent, right? 3 and then the e and then 8 this time, right? Because it has 8 zeros after the 3, so it is 10 to the power of to the 8th. Does it make sense? So in stuff, if I say, okay, I only need to get a rough estimate of the numbers, you can just say, oh, this is the same thing as 3E8 on a calculator, which takes a lot less time to punch compared to typing this entire thing in, or 3 followed by 8 zeros. Do we agree on that? Yes? Okay. So let me just kind of write down on a notepad what I mean by that, okay? Because this way it would be a lot more clear. Okay. So we'll look at the number, okay, as it is, and I say, oh, if I don't really need all that precision, I can just enter 3E8 on a calculator. Does everybody understand what that little e is representing when you enter that in a calculator? Some calculators has it spelled out as EXP. Some calculators have it spelled out as what? Pull out your fancy TI calculator. What is labeled? What is the label on that key? Just E? Hmm? 2E, okay. So EE or EXP, it depends on the brand of calculator. Casio has a slightly different, nomenclature compared to TI. So what does yours say?
I think it's EE as well.
Okay, so TI uses EE. I think Casio calculators use EXP, okay? So there's a little bit of variety there. But what does it mean? What is the E doing in this particular case?
10 to the...
Exactly. So it's separating the power of 10 from the mantissa. So in this case, 3 is called the mantissa, which is usually a number from, in base 10, it's usually a number from 1 to almost 10. Okay, if it's normalized. So so it can range from 1 to 9.999999 for the mantissa, which is the 3 part here. The E is actually a separator. That's all it does, is to separate the mantissa from what we call the exponent of 10 in this case. So 3e8 is a very simplistic notation to say, oh, this is actually what we want, okay? It is 3, which is called the Mantissa, times 10. Okay, I'm going to spell out the whole thing. It's times 10 to the power of 8. Okay, I'm just spelling out the whole thing, the whole power thing. So the first number, the first parameter is what thing raised to which power, which is the second parameter. Is that okay? Are we okay so far with what this notation is representing? So can someone answer the question again? Why do we prefer 3e8 instead of 3 and then followed by 8 zeros? Yep. It takes up a lot less space, okay? And someone may argue and go like, well, 8 zeros I can do, okay? Not a problem. What about the size or the dimension of an electron? Let's look it up, okay, and see whether you guys want to enter that without using the scientific notation, okay? So we'll look up size of electron. There we go. So the size of an electron is, where is it? It doesn't have a size, does it? It is, well, it does have a mass, okay? So let's say we're trying to enter the mass of a single electron. Does anyone want to do a 0 point and then put in 30 zeros and then 9109? Can your calculator let you specify that many zeros after the decimal point? But you don't want to, exactly, because now you have to count the zeros, okay? Counting 30 zeros is not that easy, okay? So that's why we like to use the scientific notation, because to enter this number or this value on the calculator, it is 9.109, and then press the EE button, on your TI calculator, -31, done. Okay? That's the use of scientific notation. So what is magical about the scientific notation? Why is it so cool? It separates it separates the value into two distinct parts. One part is specifying, okay, give me a number between 1 and 10. Okay? That's pretty easy to enter, right? A value from 1 to 10, especially when you only need like 3 digits after the decimal point, okay? We can get that done easy. And then the EE part, or the E part, when we type it out using a text editor, is the separator between the Mantissa. In this case, the Mantissa is 9.109, and the exponent of 10 that controls the magnitude of the number or the value that you're trying to specify. Is that okay? So when we are trying to talk about the net worth of Bill Gates, do you want to spell out the entire thing, or do you just want to say, oh, here's his net worth is, I really have no idea. Let's just say it's 20 billion, okay? Well, 20 is kind of the Mantissa. It's not exactly, but the billion is specifying, oh, it's 10 to the power of 9. Is that okay? So the idea is we separate a value into one part that has some precision to it, which is the Mantissa, and then the other part just specifies, oh, by the way, multiply that value, which in base 10 is usually between 1 and 10, by this gigantic value, which is a power of 10. So are we okay with that concept? Yes? Okay. If we can use that concept, breaking a number into a Mantissa times 10 to the power of some number, do you think we can borrow that idea in base 2? Well, there's no reason why we cannot, okay? So let's take a look at some number or some value expressed in that particular way. Okay, so we're switching to base 2 now. So in base 2, I can specify 1.01101, okay, and then times 2, okay, I have this emphasize, this part is base 2, and times 2 to the power of 1001, and this is also in base 2, okay? So now we have a Mantissa that is specified in base 2, and then we also have an exponent that is also specified in base 2. Is that part okay? Okay? But exactly what value are we talking about here? Can we convert this back into base 10 so we can actually take a look at what is the exact value? Sure. Okay, 1 is 1, okay? What is that 0 doing? What power of 2 is the 0 to the right hand of the decimal point trying to specify? How many 2 to the power of negative 1s, okay? And, well, we got none of those. But do we have a quarter? And so the quarter is indicated by this 1. So we got a quarter. Okay, so we say we do have a quarter. Do we have an eighth? Yep. Okay. Do we have a 16th? Nope. Do we have a 32nd? Okay. I think a 32nd has a lot of digits, so I'm just going to say 1 divided by 32. Okay. This part here, this entire part, is the mantissa. But we have to multiply the mantissa to 2 to the power of, what is 1001? 9. Okay, very good. So it's just base 10 in 9. So this is kind of the value that we want to represent. So you have 2 ways to handle this one. Okay, so one way to do this, which is kind of the lazy way, I'm going to rewrite this part as just a base 2. And we can shift, okay? In other words, what happens to the mantissa if I say, let's multiply the mantissa by 2? What do you think it's going to look like? The decimal point shifts 1 place to the right. Okay, that's exactly what happens when you multiply just the mantissa itself by 2. Because 2 is the base of the number. So when you multiply that by 2, okay, it becomes 10.1101 in base 2. But if I multiply the mantissa by 2, what do I need to do to the exponent of 2 in order to maintain the same value? Decrease that by 1. So is this part okay? Does everybody understand why I can move the decimal point by 1 and then adjust the exponent of 2 also by 1? Yes?
Could you review the explanation?
Okay, sure. So the question is, what is 10 in base 2? In base 10?
2.
Yep, okay. So if that is the case, can I specify this? So this is kind of the intermediate step that I did not mention. Is that okay? Now, if I do this, I have to adjust the exponent, right? In other words, this is specifying 2, right? This is specifying a half. They cancel out. Is that okay? But when we do this, if you look at this, just the product of this in base 2, what do you think that product is going to be? We're just focusing on the highlighted portion. Do we kind of have an intuition that this would look like 10.1101? That's it. That's how we shift the binary point. Note how I did not say decimal point because this is a binary number. So we shift the binary point to the right by 1 when we multiply 2 to the mantissa. Is that okay? But the other side also has to change because when you look at the product of these two, okay, which is 2 to the power of 9 times 2 to the power of negative 1, what is that? 2 to the power of 8. And that's the reason why we end up with this line here. Is that okay? So a lot of the things that we know in base 10 also works in base 2. Is that okay? So we can use this trick again. Okay, so it becomes 101.101 in base 2. And then the power of 2 go down by 1. And you can kind of see, this gets a little bit boring because all we are doing is to keep shifting the binary point. Okay. 1010.1 in base 2 times 2 to the power of 5. And now it becomes 101101 in base 2 without the binary point anymore times 2 to the power of 4. Are we doing okay so far? Yes? Okay. So at this point, I can work with just integers. I just don't like to work with fractions. So I can now work with integers, or I can continue and just say, oh, we got times 2 to the power of 4. We can just add 4 zeros to the binary number and call it a day. So let me just kind of finish that representation. So this whole thing just becomes 101101, 1, 2, 3, 4 zeros in base 2. We good? And exactly what value is it representing? Let's go ahead and check this out. Okay, so it is, we have no 1, 2, 4, 8. We got 116, no 32, 164, 11628, no 256, and 1512. That's basically what the value is representing. So we can totally start with a base 2 quote-unquote scientific notation and turn it into the value that it is representing. So we do have a little bit of base conversion at one point, which is the very last step. But other than that, everything in between is something that you already know how to do in base 10. We're just extending those approach in base 2. Are we doing okay so far? So you can also kind of imagine that if I allow a pretty good range when it comes to the exponent here, like give it 11 digits in base 2, then I can specify a pretty wide range of values. Does it make sense to you? On the other hand, if I extend the Mantissa so you can have up to, let's say, 53 digits, then I can specify very small differences between values. So one value versus the one next to it can be very, very small in difference because we are talking about 1 bit in 53 in this case. So we can have values that are very close but not exactly the same in order to kind of work out scientific calculations. Are we good so far? All right. So I think we are ready to get back to the notes in order to understand what is the double precision floating point number representation. So let's see. Yep, this is the module. All right. So we'll go kind of slow. We'll go step by step. So a double is basically the abbreviation of double precision floating point number. The full name is IEEE, double precision floating point number, and then IEEE is the International Electrical Engineering. Okay, I cannot remember the full name of IEEE. So if you really want to spell out the entire name, then it is, okay, where? On the right. Oh, okay, thank you. So the full name of double is the Institute of Electrical and Electronics Engineers Double Precision Floating Point Number. Can we agree to call it just double? Okay. So from now on, we just call it double. All right, so what does it mean when we say double? It's a format. In other words, it is a way of looking at bits and say, what is this bit doing here? What does it mean? Okay, how does it change? What part does it play when we try to specify a value? That is the format. Okay, so the first thing we start with is how big is a double? Okay, a double has 64 bits. Okay, and since each byte has 8 bits, we can also say a double has 8 bytes. Is that okay? Okay, that's just how big it is. So what else do we need to know? So in this discussion, we use f subscript I to refer to bit I of the double, with a bit pattern of f. So when we refer to f, we're referring to all 64 bits. When we say f subscript I, we're referring to one single bit. Is that okay? It's kind of the same notation that I use for X, Y, Q, and so on. The subscript is just indicating which bit position I want to focus on. All right. So using that notation, then we will look at bit 63 first, okay, or F subscript 63. That is known as the sign bit. And the way we look at the sign bit is pretty easy. It's somewhat consistent with the way we look at signed number representation, where if the sign bit is a 1, the value being represented is negative. When the sign bit is a 0, then the value being represented is non-negative. Is that okay? So it's definitely a binary thing. Is it negative or not? Are we good with the sign bit? Yes? Okay. So that's bit 63. That's all it does, is to indicate the sign of the value being represented. Bit 51 to 61, there are 11 bits here. And what it does is a little bit more complicated. So the first thing we'll do is to look at this portion here. Okay, just look at the equation that is highlighted or selected. So what we do is we first come up with lowercase e, okay, which has nothing to do with the e in a scientific notation. I just choose to use a variable named e in this discussion. And the way we do it is a sigma notation, which means we have a loop to specify terms, and we want to add up all the values of the terms. Okay? So how many terms are we dealing with? The index goes from 0 to 10 inclusively. So how many times do we go through the loop? 11 times. Okay, so I goes from 0 to 10. So there are 11 iterations or 11 terms in this case. What does each term look like? Well, this is what each term looks like. Okay, F subscript 52 plus I times 2 to the power of I. That's it. So all it really is saying is, okay, let's just take a look at bit 52 to bit 62 and treat it as an unsigned integer, and we want to find out what the unsigned value of those 11 bits is. That's what this equation is trying to say. Are we good so far? Yes? Okay. But that is not the end of the story, unfortunately. So can E be negative? Just look at the term here. Can E be negative? Is there any subtraction involved here? No. And can any of these terms inside each product be negative? No. So that means E itself is non-negative. It is an unsigned interpretation of those 11 bits. Bit 52 to bit 62. Are we good so far? Well, that wouldn't be very helpful because we would like to express the mass of an electron, which definitely is not going to have a positive exponent. It's going to have a negative exponent, right? So that means E itself is not the final answer. The actual exponent of 2 is what I use E2 for. So let me highlight that portion here. So the actual exponent of 2 is this term here. We take the E that we have, the E that we have, and then we subtract 1023 from it. And that 1023 is a base 10 number.
That 1023 is the same no matter how many.
The number of bits is fixed to express the exponent. So if you look at the range of an 11-bit unsigned interpretation, what is the range of E itself as an 11-bit unsigned number? It goes from 0, right? Because if all 11 bits are 0, it's represented with the value of 0. But it goes up to how much? 2 to the power of 11 minus 1. Yep. And what would that be? 2 to the power of 11 is 2048, right? 2048 minus 1 is 2047. So E itself, okay, when you look at E itself, it has a range from 0 to 2047. Are we good so far? But E2 is E minus 1023. So what is the range of E2? It would be from 0 minus 1023 to 2047 minus 1023, right?
Oh, E2 is just like the second. I thought it was like E subscript 2.
It is E subscript 2, right? Yep. So E2 has a range from negative 1023 to positive 1024. Okay, that is the actual usable range of a power of 2 that we multiply to the mantissa. Is that okay? That's a pretty wide range. Okay, that is a pretty wide range already. Do we have any questions about this part here, how E2 is derived? I have a question. Why don't they just use the signed representation and just look at the 11 bits as a signed number, and then we just, then we naturally have a range from negative 1024 to positive 1023. Does that make sense to you? Because if you look at 11 bits using the signed interpretation, the most negative value is negative 1024, the most positive value is 1023. Then you might argue, but it's off by 1 compared to this particular scheme. Yes, it is off by 1. It's not a big deal. Okay? So my question to IEEE is, why do they use the biased representation instead of just a signed representation? I kind of have the answer already, because they are a bunch of electrical and electronic engineers. They're not computer science people. It's a joke. It is specifically directed to kind of insult EE people. But no, but it is a valid question, because the sign representation is a great way to look at the value, based on the fixed number of bits. We just say, okay, this is how we interpret the value of those bits, so that we can have both negative values and positive values. This is doing about the same thing, but it's not exactly the same thing. Okay, so that's kind of, it's puzzling to me.
Maybe there's some hidden factor that makes this easier to represent physically.
I cannot really imagine how. But the IEEE's double precision floating point number has been around for a long time, so possibly longer than the use of 2's complement for negative values, to negate values. So I don't know exactly what the story is. It's just that it doesn't seem to make sense to me. Okay, so here's the mantissa. Okay, the mantissa bits. Okay, I will put mantissa in this case in double quotes. Okay, so the mantissa in quote bits are from bit 0 to bit 51. So there are 52 bits for the quote unquote mantissa. Now, why do I say mantissa in quotes? Because those bits are only the fractional bits of the mantissa. There's always a 1 point that is implicit. So the actual mantissa in base 2 has a fixed 1 here, and then plus a whole bunch of terms that involve the bits of the floating point number. Is that okay? So this 1 is always here, and then plus a whole bunch of terms that is based on the bits actually in the number itself. What is the largest power of 2 when you look at the sigma notation? Okay, so look at the index here. So I goes from negative 52 to negative 1, and then the power of 2 is just I itself. So what is the largest power of 2 in the entire sigma term? Negative 1, which is a half, right? So that means even if you have all the bits from bit 0 to 51 all being 1s, okay, the sigma term will only return a value that is pretty darn close to 1. Because it's 1/2 plus a quarter plus an eighth plus a 16th plus a 32nd plus a 64th and so on. It will never get to 1. It will get pretty close to 1 but not 1. Does it make sense to you? So the sigma term is added to a 1, so that we actually end up with 1 point, blah, 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 blah. Okay? So if you are to write out, what a number is going to look like, this is what it is going to be like. Okay? So the mantissa M2 is basically 1 point. The 1 point is always there. The most significant digit on to the right-hand side of the decimal point is going to be F 51, okay? The next one is F50, the next one is F49. I cannot do subscript, so just kind of imagine the digits are subscript, okay? Plus, F49, 48, blah, 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 all the way F2 down to F0, okay? So as I said, bit 0 to bit 51, they're all fractions of the mantissa. So now the question is, why do we always have this one point here? Well, we'll find out why later on, okay? So for now, we just have to understand that is basically how we represent a value using double. Are we okay so far? Yes? Okay. So now we want to look at an example, okay? Because going through this discussion can be confusing, so we want to look at an example, okay? So we'll look at an example and say, okay, how do we represent it using double? So we can start with something. We can start with something big, okay? It's easier looking at a value that is larger than a value that is smaller, okay? So let's say we are just looking at 317, okay? In base 10. This is in base 10. So now we say, okay, how do we convert 317 into a double representation? That's the question. Well, as you might imagine, the first thing you might need to do is to convert 317 into a base 2 representation first. Is that okay? So I'll just do it really slow because my arithmetic is pretty rusty. We know it has 256. So once we take care of the 256, we got, 61 left? I think so, right? And once we see that, what is the next power of 2 that we need to include here?
64.
No, it does not have a 64 because 32, thank you. So it would be 32 plus, I think it's 29, yes? 32 plus 29 is 61. So I'm just working with one power of 2 at a time just because I cannot mentally track multiple digits at the same time. So 29 has what? 16. 16 is the largest power of 2 that is less than or equal to 29. So we got a 16, which has a leftover of 13 now. And we look at 13, it has got an 8 and then the 5. And then we are all done because a 5 has a 4 and a 1. Is that okay? So now we convert this. And to convert this, it is usually best to, well, there are several ways to do it. We look at 256, which is 2 to the power of 8. As a binary number, it would be 1 followed by how many zeros? We talked about this when we talk about base conversion. So we're looking at 256, which is 2 to the power of 8. If I want to write it out as a binary number, how many zeros are to the right-hand side of 1? No, it's the same number as the power of 2, okay? So 2 to the power of 8 is going to be 1 followed by 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8, okay? What about 32? Well, it would be 1 followed by 5 zeros. Very good. So we look at 1, 2, 3, 4, 5. And this is the place where we put a 1 so that we end up with 5 zeros. I just want to line everything up. All right, so what about 16? Oh, that's an easy one. 16 is 2 to the power 4, so we leave 4 zeros and turn this into a 1, pad the rest with zeros. What about 8? Okay. What about 4? And then we have 1. Okay. Do you think you need to know or be reminded how to do all the carry stuff in binary addition for this particular addition? No, we we do not need to know about carry because we only have up to 1 1 per column. There's no carry whatsoever. So when you add all of these up, you just get 1, 0, 0, 1, 1, 1, 1, 0, 1 in base 2. Is that okay? So we have just converted 317, which is a base 10 representation of the quantity that we want to represent, into a binary representation, which is 1, 0, 0, 1, 1, 1, 1, 0, 1. Okay, a lot longer, but it's really representing the same thing. What do we do next? Well, this is the cool part. We just say, there's an implicit point here. Does anyone want to disagree that I can just put a point there? Okay, I can always put a point there because this particular one is the number of ones. Okay, well, just because this number has no fractional part or the fractional part is 0 doesn't mean that I cannot just put a point here. Okay. So now I will just kind of do a dot 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 here, and I'll let you guys answer that question. 1 1 0 1 1 1 0 0 1 1 1 1 0 1. Okay. So if I shift that point, okay, this many times, then what do I need to compensate by multiplying a power of 2? So I'm asking, what is the power of 2 that I need to multiply to this particular value in base 2 to compensate for shifting the binary point all the way to the other side? Okay, what do you think? Every time yeah, go ahead. 8, very good. Well, I don't really know because I have to check. So we have to count. So we have 1, 2, 3, 4, 5, 6, 7, 8. So we have to shift the binary point exactly 8 times to come to 1.00 blah blah blah, okay, which is the normalized mantissa that we want, okay? But every time we shift the binary point to the left by 1, we have to compensate for, because that's the same thing as multiplying the mantissa by a half, right? So I have to compensate by increasing the exponent of 2 by 1 every time we shift by 1 position. So this time, we have a 2 to the power of 8. Is that okay? Is all the math still working? Because we still want to represent exactly the same value. We're just chopping the representation now into 2 parts. Here's the mantissa, which is from 1 to almost 2, and here's the exponent, which is just some number that we have to represent separately. Is that okay? All right. Oh, but 8 is not a binary number. Okay, we can try to convert that, right? How about looking at 8 as 1, 0, 0, 0 in base 2? Okay, because 1, 0, 0 in base 2 is 8. Is that okay? All right. So what have we found out at this point? E2 is 1, 0, 0, 0 in base 2. That's what we have found out. Because that is the actual power of 2 that we want to represent in a double. But Tak, you mentioned earlier that we use E as a in binary to represent the exponent in a double. This is just E2. How does E relate to E2?
E2 was E minus 1023.
Yes, so E2 is E minus 123, which means E is, help me solve this equation. E2 plus 1023. Would that be okay? 1023, right. Okay, so that means E2 is 8 plus 1023. I'm shifting back into base 10 by the way. Then we can convert it again. Which is what? 1031, okay, in base 10. And 1031 in base 10 is 1024 plus 7, right? And 7 is cool because 7 is 4 plus 2 plus 1, right? All powers of 2. Basically, it's just 1, 1, 1 in base 2. So now how do I look at this as a base 2 number? It would be 1 followed by how many zeros? 1024 is 2 to the power of 10. So it's a binary number. How many zeros are we looking at? 10 zeros. Very good. Okay, so we'll pad the zeros first. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, in base 2. And this is the 1, this is the 2, whoops, and this is the 4. Is that okay? So, yeah, this number is particularly easy to convert, but that's kind of, what we're working with. Is that okay? That's E. That's E2. Oops. I think I messed up a little bit here. That's E and not E2. Sorry about that. Okay. That's just E. So strike out the 2. There we go. All right. Is the value we want to represent negative or not? Nope, it's not negative. So the bit 63 is going to be a 0, because if it is a 1, it's non-negative. Excuse me, if it's a 1, it is negative. If it is a 0, it is non-negative. Okay, very good. What about bit 62 to bit 52? Yeah, that's kind of cool, right? Copy and paste. Cool. What about bit 51 down to bit 0? What would those bits look like? Remember, it's the fractional part of the Mantissa. The Mantissa is, by the way, still on the projector. Where is it? This whole thing is the Mantissa, but the 1 point is not represented in the bit pattern. So we only copy this part to here. Is that okay? So bit 51 itself is representing the halves of the Mantissa. So that means, we don't copy the 1 point. This part is always implicitly there. We only copy from this point and on, okay? So we copy that, we paste it in here, and then we just go like, wait, there are supposed to be 52 digits here, and we only see how many? We only see 8 digits. Where's the rest? Fine. So now we have, we'll call this 52 digits, okay? The most important part will be the most significant portion, because the rest are all zeros. We just pad it with all zeros. Is that okay so far? I think we have just figured out all the bits. We got bit 63, we got bit 62 to 52, we got bit 51 down to 0. We got all 64 bits. Cool? So what is that going to look like? Well, it's not going to be very exciting. If you're thinking about, oh, this has got to be exciting because we're working with double, no, this last part here is super duper boring. It's just concatenation. It's just 0 followed by this portion followed by this portion. Now, how boring can that be? It is super boring. It's just concatenation. Okay? So now we have 64 bits, and I claim that these 64 bits together will be representing 317. Okay? So what are you going to do? We want verification, right? We want a proof that this actually, at least it works for this case. Okay? We need some kind of validation. Okay. So what do we do to validate this? Okay. The first thing I want to do is to, instead of having to type in 64, individual zeros and ones, let's find a better way to represent this. Okay. It's called hexadecimal. So in hexadecimal, what you're doing is you are chopping up a bit pattern into chunks of 4. Okay. And for each chunk of 4, you look up a table and you find out what is the hexadecimal digit corresponding to it. 0100 is a 4, 0000 is a 0, 0111 is a 7, 0011 is a 3. Those are all the boring ones because we have all of those in base 10 as well. This is a good one. 1101 is what we know as 13 in base 10, but in base 16 we want to represent the same quantity using only 1 digit. It'll be the uppercase or lowercase d, okay? So now we have 7 digits done, and how many digits are taken care of? 20 digits, right? So we have how many more digits to take care of in hexadecimal? We have 44 digits left, but those are bits, right? We have 44 bits left. But when we convert everything into hexadecimal, 4 bits turns into one single hexadecimal digit. So in hexadecimal, how many zeros are we looking at? 11 digits, 11 zeros. Okay, that's pretty easy to type. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, we're done. All right, so now we look at this bit pattern here, expressed as a hexadecimal representation. It would be 0x, which is the prefix of a hexadecimal number in C and C++, and most other programming languages. 4073D, and then 11 zeros. Okay, and I claim that this is representing 317 if you choose to look at the bits in a double format. So how do we check that? Yes?
Question. So is the double format always 64 bits?
Yes. So internally to the computer, each double variable always uses 64 bits or 8 bytes to represent.
So I know you were saying for like when we were assigning integers that the architecture can dictate how many bytes an integer takes up.
For a double, it is not that case. For a double or single precision number, so a single precision a single precision floating point number is known as float in C and C++, and a double precision floating point number is known as a double in C and C++. There are bigger ones too. I think there's one floating point representation that uses 128 bits, but we don't use it, anywhere, practically. So double is the most common format if you need to represent constants in science and do all that type of calculation. Yes?
So a double is unique to like a 64-bit architecture?
No, it is not. Let me explain that. Let me qualify that statement. And I just need to move this thing to here. There we go. Okay. All right, so the question was, is a double specific to a 64-bit architecture? Would that be the answer, the question? Okay. The answer is no. You can actually use an 8-bit architecture and do math in using double as variables and do math. It would just be very, 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 very slow. Because with an 8-bit architecture, you can only add or subtract 8-bit at a time. The Mantissa itself is technically 53 bits wide. So that means you have to use, 53 divided by 8, and take the ceiling of that is 7. 7 times 8 is 56, right? So it will take 7 individual additions to add the Mantissas of 2 numbers. So it will be really slow, but it can do it. In the good old days, before we had floating point processing units, the FPU, we only use integer math to deal with double or single representations, and it takes a long time to do all those calculations. And that's why in the good old days, in the up to the 486 processors, people used to buy what they call a co-processor, so they can do all the math stuff fast. Okay. So we got 5 minutes left, and let me double check on the time because the clock sometimes is off. No, we have more than that, right? Yeah, we got 15 minutes. We are getting out of here by 11:50, so we got 15 minutes. Okay, that's plenty of time for what I need to show. Because I look at the clock, it says 10:15, so my so I thought it's a Thursday class. I have to end the lecture at 10:20. So I thought I only got 5 minutes left. But as it turns out, I got plenty of time. Okay. So now we'll write the sample program. I'm not sure whether that sample program is still here or not. It is still here. Okay. So we can just reuse it. This is the program. Okay. What does it do? Not a whole lot, right? I mean, just look at this. If pound includes not standard I/O, it's standard integer. STDINT stands for standard integer, which is really just a header file with a whole bunch of macro definitions and type defs. Okay, all it does is so that we can do something like this. We want u as a variable to be a 64-bit unsigned integer. Okay. Now, if you are using a 64-bit architecture, which I'm using right now, and you just declare unsigned, it probably will give you exactly the same thing. But the point is, I want this program to be cross-platform compatible. In other words, if I cross-compile this program to a smaller architecture, like a 32-bit platform, I still want u to be a 64-bit unsigned integer. If I want to cross-compile this program using the Arduino, I still want a 64-bit integer. This guarantees that. If you just say unsigned, then the width of that unsigned depends on the target of your compiler. If your compiler is targeting a 16-bit system, your unsigned is probably just a 16-bit unsigned integer. If your target is a 32-bit system, then your unsigned is probably a 32-bit integer. But if you say uint64_t, it guarantees to be a 64-bit unsigned integer, regardless of the target of your compiler. Okay. Some of you have some exposure of why we have quote-unquote cross compilers, because when you are using Arduino, okay, you're compiling code to run on a very small 8-bit processor. So even though the host, which is running the IDE, may be a 64-bit architecture, the object code is going onto an 8-bit architecture to execute. So that makes the Arduino compiler a cross compiler. Okay. I can talk more about embedded systems and cross compiling and why it is really interesting and useful, but on another day. So this program doesn't do much. I just say u equals to 0, because if I don't do something with u, the compiler is smart enough to optimize it out. So I cannot really test stuff. Okay. So all this statement does is to trick the compiler into keeping the local variable u. Okay. And then we have a return. The program doesn't do anything. Okay. Do we have any questions about this particular program? Okay. So we run the compiler. Okay. GCC-G to include debug information. Warn all. You should all be using it if you have an option. Test is -o, which is specifying the output, the name of the executable. Test.c, which is the source file. Okay. And it gives me a warning. And the warning says, variable u is set but not used, which is basically saying I put a value into the variable, but I never refer to the variable. So it's the compiler saying, hey, maybe you intended to use this variable somewhere. I'm just warning you that you have one variable that is not used. Maybe it's a mistake. Okay, you might want to double check. It's just a warning. But in this case, the warning is okay, it is not a mistake. So now we get into GDB, which is the debugger. You can do really the same thing in CodeBlocks or some other IDE, okay? Because CodeBlocks is really just an IDE on top of GCC, G++, and GCC, G++, and GDB. Okay, so I'm just using all the low-level tool that is behind CodeBlocks. Okay, so I list the program, put a breakpoint on line 8, run the program, and we print u. It is just 0. Okay, not surprising. Is that okay? Right? Okay. So I can also print the size of u, and it says 8. Well, that makes sense, right? Because u is a 64-bit unsigned integer. It has 64 bits. 64 divided by 8 is 8, because there are 8 bits in a byte. Okay? So everything seems to work. So now the question is, how do I check whether the conversion that I did earlier is correct or not? Okay? In other words, we look at this number. Okay? So let's put everything together. 4, 0, 7, 3D, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay? And this is a hexadecimal number. Okay? All right. So we take all this, Control-C to copy, go down here, and we say set var u equals to that thing. Okay, so I'm gonna do a paste. There we go. So this is a GDB command. GDB is kind of nice, you can examine the value of a variable, but you can also change it when you're on a breakpoint, okay, which is really useful because if your program doesn't do anything, it's doing something that's wrong, and you catch it at the point before it does any further damage, you can kind of nudge the value back to where it is supposed to be, so you can continue to run the program to find the next bug, okay? But this is something that we can do. Okay, so we press the enter key, okay, everything is good. We say print x, /xu, which is, the /x means use hexadecimal as the format, okay? And we get it back, not a problem. Now in GDB, it also gives you a /t, which is binary, which is kind of cool because we can now see the entire number in binary, except the leading 0 is missing, okay, because it doesn't need to print a leading 0. Pretty sure there's a way to specify let's print the leading 0 too, but this is without the leading 0. Are we doing okay so far? Okay. So we know the bit pattern is in U. Now the question is, but how do we check whether this particular bit pattern is representing the value of 317? That's the question, right? So let's try a few things first, okay? So we can say, let's cast it, okay? Unfortunately, cast is not going to work, and I'll explain why it won't work. Then we'll look at the actual result of this particular expression. So when you look at this cast operation, the first thing it encounters is U, okay? Because the compiler doesn't always read or parse from left to right. It interprets in various orders. So in this case, it will try to figure out what U is first. Now, when you just say U, do you think it's referring to the value of the variable U, or do you think it's referring to the address of U? The value. It's going to be referring to the value of U. So it looks at U and go like, okay, I will retrieve the value of U, which is this whole thing, or this whole thing interpreted as an unsigned value. That is what U is going to return, or variable U. And then it will try to do the cast operator, which is basically saying, okay, now we take that value and convert it into a double representation. So what it is doing is really just this, which is not what you want. Because if you say print U without using /x, you can see that it gives you the same thing. This is the unsigned interpretation of the 64 bits. Is that okay? But that's not what we want, okay? Because we want to look at those 64 bits, but using the interpretation of a double. We don't want to look at the most significant bit and say, oh, this is specifying how many 2 to the power of 63s do we have. That's the wrong interpretation. That is just a sign bit, okay? So how do we change the interpretation? How do we convince GDB to change the interpretation? Okay, I'll do this step by step. This is U, and what is that? The address of U, which has a type of, it's a pointer, exactly. So it's a pointer to a 64-bit unsigned integer, okay? Can we typecast a pointer into a pointer of another type? Yes, okay. So I take this and say, yep, I know this is the address of a 64-bit unsigned integer, but let's pretend that it is not. Let's pretend it is the address of a double. Now, it's relatively safe in this case because they both have the same size, so I don't have to worry about, are we looking at the first half or the second half? Well, they're both 8 bytes long, so we're still referring to the exact 8 bytes, but we are saying don't interpret it the same way. Okay, now we're specifying a different way to interpret it. But we are not done yet, because if you do a print here, it's just going to print out the address of U, right? It's like not going to be very helpful. So we have to dereference it, right? So we have to do a dereference of this thing here. Huh? What?
Because it's a pointer to a double.
It's a. But this is what I want. Okay, this is what I want because we start with U, okay? Then we tell GDB, but it's not the value of the variable that we want. I need to know where you are. What is your address? That's ampersand U, right? Well, ampersand U says, okay, here it is. This is the address of a 64-bit unsigned integer, okay? Then I go like, no, I don't want to look at this as the address of a 64-bit unsigned integer. I want to look at this as the address of a double. That's what the cast is doing. It's casting the address, it's not casting the value. Okay? So when we are done with this, okay, everything in the parentheses, we now end up with, okay, now we have the address of a double. Okay, it's just an address, just like the address of anything else. Then I go like, okay, tell me what is there. Now, because of the type of the pointer, when I ask, tell me what is there, the interpretation is now based on the pointer type, right? Because it's a pointer to a double, when I ask what is there, it's going to use the double interpretation. It will look at those same 64 bits, but not as an unsigned 64-bit number anymore. Now it will look at those 64 bits and say, I'm going to treat this as a double. Bit 63 is just a signed bit, no big deal about that one. Bit 52 to bit 62 is my E. Bit 0 to bit 51 is the fraction of the Mantissa. Now it knows how to chop it up and interpret all of those chunks. Is that okay? So now when I press the enter key, what should I see? The value. Yep.
Dark blue, is that
Yeah, that's just the address. It's 7FFF blah 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 blah. So it really is just the address of. Oh, it doesn't show it. I was hoping when I highlighted it would it would invert the color, but nope, it does not. Okay, but it's really just 7FFFF E1A8, which is an address on the stack. Is that okay? So this is kind of a way to verify the way we interpret the double is correct. Okay, so all of those steps that we talked about earlier can now be verified and go like, oh, okay, we did get 317 back. Are we doing okay so far with this? So today's lab is for basically it's just setting you up to understand how to work with powers of 2, exponents, and stuff like that. So before we leave, this part I'll just kind of write on the board here because it's just a reminder. You might want to know how to take the log 2 of a number. So what is that? Your calculator probably does not have a log 2, probably has a natural log, right? So it's just, you have to take the natural log of x and divide it by the natural log of 2. That becomes the log of base 2 of x. Okay, so you kind of need to know your basic math about exponents and logs in order to kind of get the homework the lab going. But other than that, today's lab is supposed to be pretty short, and it has no circuitry, so you don't have to work with Logisim today. All right, so I'll see you guys over at the lab, and I'm going to stop the recorder first.
My memorization of log laws is